Okay, so what I have here is a barometer problem. So let me just quickly explain how the barometer is set up. So what we have when we have barometer is a dish that is open to the atmosphere. So all around here is just the air and atmosphere. And the atmosphere will push down onto a dish filled with mercury, and in the middle of the dish is a vacuum vial, container, upside down tube, and what happens is as the atmosphere pushes down, it pushes the column of mercury up into this tube to some type of a height. Okay, so that is what we're going to be looking for. Now, in our specific problem here, the atmosphere is not one atmosphere like it would normally be, or 1 × 10⁵ Pascal, but instead we're in a catastrophic hurricane, and the pressure is 920 millibars, or 0.91 atmosphere. Either way, neither one of these units are what we want to be using for our problems. We want our answers in pascals. So 0.91 atmosphere would equal 0.91 times 10 to the 5th Pascal. If you're reading a barometer, how high would the column of mercury be? So what we want to talk about is how this is not a moving column of mercury, instead it's at rest. So if we have this equilibrium happening, the atmosphere is pushing down here. It's going to be at this point here exactly what it's feeling going up, whatever the atmosphere is feeling going up. So it's just in an equilibrium. So atmosphere pushing down is atmosphere going up, and we can say that the pressure here at 0.1, I don't know why I wrote it high, 0.1, is going to be the same as the pressure here at pressure 0.2. So P1 is equal to P2. P1 is the pressure of the atmosphere, because that's all that's going to be here. So I'm actually going to put atmosphere in this situation because we want to make sure that we're using the correct thing. Okay, then we want to set that equal to P2, which above this point, P2 is only mercury, right? Because this is a vacuum. It was a vacuum tube to begin with. So this is not air inside of here. There is no air. It's all a vacuum. So the only thing above this point is mercury. So, and there's no P naught plus our gauge pressure. It's just going to be the density of the mercury times G times the height of the mercury, which is what we're looking for. So height of the mercury, if we rearrange, is going to be the atmospheric pressure at the time over the density of mercury times G. Now don't forget, P atmosphere is usually 1 times 10 to the 5th, or 1 atmosphere, but in this specific problem, it is 0.91 times 10 to the 5th Pascal over the rho of mercury, which is given in the problem. Multiplied by 9.8 meters per second squared. And I get for my height of my mercury to be 0.68 meters, or 68 centimeters. Now, if you are taking a chemistry class, or maybe you've heard of different types of units for things, right? And just in this problem alone, we talked about the bar, we talked about atmosphere, and we talked about pascals. Well, there's also a way to measure atmosphere in centimeters Hg. So centimeters Hg is going to be your centimeters of mercury. So we got 68. 1 atmosphere is equal to 76 centimeters Hg. 76 centimeters Hg. So we are getting something significantly lower than that, which makes sense. Because if all of a sudden this mercury is pushing on here less, then we're going to have less of an atmosphere pushing up at this point. I drew it quicker, but I was just trying to, less of a pressure pushing up at this point, and we will not rise as high. So we're going to be a lot lower than a normal atmospheric pressure. All right, hope this helps.